Read this sentence slowly. The cat ate the mouse because it was slow. Now, a simple question, this little word it, who does it point to? The mouse? Or the cat? You answer without even thinking, the mouse, of course. It was slow, so it got caught. But pause for a second on what you just did. You linked one word, it, to another word, 6 words earlier, using the meaning of the whole sentence. For you, it's instant. For a machine, it's a real puzzle. And the way modern AI solve it has a name: attention. That's our topic today. To feel the challenge, put yourself in the machine's place. At first, to it, a sentence is just a string of symbols. No meaning, no grammar, no idea who ate whom. And it is an especially tricky word. Here, 2 candidates, the cat and the mouse. Grammar alone won't decide. Change a single word, the cat ate the mouse because it was hungry, and suddenly it is the cat. The right link doesn't depend on grammar, it depends on meaning, on context, on the logic of the scene. First step, split. An AI doesn't read words the way we do. It breaks the text into small units called tokens. Often a token is a word, but not always. Watch our sentence split apart, the cat ate the mouse. Each block becomes a piece the model can handle. The sentence is no longer a continuous line, it's an ordered sequence of tokens. Second step, and this is where the magic starts, giving meaning to each piece. A token, as is just a number in a dictionary. We translate it into something richer, a vector, a simple list of numbers, which we can picture as a point in a space. In this space, position encodes meaning. Words with close meanings become neighbors: cat and mouse, 2 animals, move close together, 8 lives elsewhere, slow joins the adjectives. These vectors are called embeddings. The key idea, meaning, has become geometry. But there's a catch. These embeddings are fixed. The vector for the word it is always the same, whether it points to a mouse, a car, or the moon. At this stage, each word lives in its own bubble, unaware of its surroundings. Yet our problem, linking it to the mouse, is exactly a matter of context. We're missing a mechanism that lets words look at each other and adjust their meaning. That mechanism is attention. Here's the intuition. Each word gets to ask a question to the rest of the sentence. The word it asks, which noun do I refer to? In the jargon, that's a query. In front, each other word shows a label, a key, describing what it offers. Mouse shows I am a noun, an animal. The machine compares the query to each key and measures their match. The stronger the match, the higher the weight. Finally, each word carries a value, the information it passes on. Query, key, value, 3 roles, 1 mechanism. Let's take the point of view of it. From it, an arrow goes to every other word. The thickness is the weight, the thicker the arrow, the more it attends to that word. At first the weights are almost equal, the model hesitates. Then the arrows adjust. Toward the 8, because thin threads. Toward cat, a real link. But toward mouse, the arrow wins by far. The model has focused its attention on mouse. The pronoun and its referent are now linked, not by a grammar rule, but by weighing all the words at once. One detail changes everything. The model doesn't do this just once. It does it several times in parallel, with what are called attention heads. Each head learns to spot a different kind of relationship. One head tracks the link between a pronoun and its noun. Another, between a verb and its subject. Another, simple nearness. Each head lights up the sentence from a different angle, then we combine all these views, that's multi-head attention. Let's zoom out. This attention is just one cog. We place it in a block, with a small compute layer, the feed-forward, plus residual connections and normalization. This block is the building brick of the transformer, the architecture that changed everything in 2017. And the secret is stacking. We repeat this block dozens of times. The early layers capture grammar, the deep layers capture meaning. This is what powers the large language models you use today. And it's not just theory. In a real model, we can visualize these weights as a heat map. Each cell says how much one word looks at another. Find the row for it, the brightest cell falls on mouse. What we drew by hand with our arrows, the model computes millions of times per second, on sentences far longer than ours. Let's retrace the path. 1. Split the sentence into tokens. 2. Turn each token into a point in a space of meaning, the embeddings. 3. With attention, each word weighs its links to the others to fit the context. 4. Stack all of this in the transformer, and understanding emerges, layer after layer. And our famous it? It found its mouse.